Hello, Professor Schumacher here. Let's do a demonstration based on VPython of the phenomenon of circular polarization of light. This is something you might come across in one of your lab courses, and it's just a fun bit of physics to understand. So here it is. This is our representation of initially a plane polarized electromagnetic wave. Please imagine that the red arrows here are the electric field vector of a wave that's propagating from left to right in this picture, and the green arrows are the corresponding magnetic field. And as you should have learned in your E&M class, for a propagating electromagnetic wave propagating along this gray line down here in the middle, the electric field is in one plane, and the magnetic field is at 90 degrees to it and in phase. And when you have that situation, then the right-hand rule of E cross B gives you the direction of the propagation of the wave. So as time goes by, you can watch the wave propagate and the electric and the magnetic field doing their thing. Okay, so that's the phenomenon of a plane or linearly polarized electromagnetic wave. But you may have seen this, like I mentioned, but maybe now you say, okay, what the heck is a circularly polarized electromagnetic wave? So in this Python demonstration, which you can pick up for yourself down, the URL is at the bottom here, for circularly polarized light, imagine that you now have a second wave, a second wave that is perpendicular to the first one, still propagating from left to right, but now the electric field will be at 90 degrees, and the corresponding magnetic field will be 90 degrees with respect to that. And we're going to put them at 90 degrees out of phase with each other. Watch this. I'm going to turn on that second wave. And now this is crazy, right? Now there's a red electric field also in the horizontal plane here that's 90 degrees out of phase with the first electromagnetic wave in the vertical direction and with the corresponding green magnetic fields. So these are two waves propagating from left to right. But as you learn, of course, in physics, is that what you actually then observe is the superposition of these two waves. So if you had an electric field meter that you could put right at this point, right at this spot right here, then what that meter would register would be the sum of the two red arrows, right? So now let's go. We're going to now turn on the total, the vector sum of the electric and magnetic field. So ready, and boom, there it is. Oh my goodness. So now it's very complicated looking, but you can see this circularity that comes in that arises simply from the superposition of the original first electric and then the second electric field waves and their corresponding magnetic fields. To make this less painful to look at, let's turn off the individual representation of the waves, wave 1, wave 2 here. And so this is it. This is what a circularly polarized electromagnetic wave looks like. Again, this is the wave that's propagating along this line down the middle here. And if you now imagine putting your electric field meter right at this point at the center, what you would find is that the electric field is of constant magnitude, but it literally rotates in space. So that's the characteristic of a circularly polarized electromagnetic wave. So how did we get here? Just to recap, we have two underlying linearly polarized waves that are 90 degrees out of step with each other, both spatially and temporally, and that sums up to this beautiful circular polarized wave. So that's really the main thing that I wanted to show you here. We now also just now want to summarize that to help fix it in our minds a little bit. So let me show you what we just mentioned. The traveling electromagnetic waves, they're sinusoidal, and the electric and magnetic fields are in phase and at right angles to each other, and they propagate in the E cross B direction, as you learn in E&M class, right? So if the electric field is oscillating in one plane, that defines the plane, or in a sense the direction of the linear polarization. And then we consider two such plane waves that are 90 degrees out of phase with each other in both space and time, and amazingly the superposition of the two waves. You can think of it as one wave, a superposition, propagating with the electric field corkscrewing through space with constant magnitude. I didn't mention explicitly, but you can imagine the corkscrew being either left-handed or right-handed, propagating in the same direction but spiraling in the opposite sense. So that depends upon the relative phase of the two underlying linear polarization waves. So those are the main points here. But there are also some things that we didn't mention that you can please ask your instructors about. So how do you make such a thing? How do you make a circularly polarized wave? And the answer is you pass the raw unpolarized light from some random thermal source through a linear polarizing filter. That's step one to get the linear polarization. And then there's an interesting gadget called a quarter wave plate, which we're not describing here, but it's a birefringent piece of material that retards the motion of one axis of the light with respect to the other by a quarter wavelength. And what comes out the other side is then our circularly polarized wave. So that's one thing you can ask about. You might wonder, what is the connection of these waves to quantum physics? And the answer is that the polarization of the waves corresponds quantum mechanically to the helicity of the photons, which is kind of a shorthand way of talking about the angular momentum that's carried by the photons. So pure states have helicity +1 or -1, corresponding to right or left-handed circularly polarized light. You can also have elliptical polarization, but that's another story. And then finally, you might ask, yeah, so what is this good for? So if you're manipulating the atomic state of the electron, the outermost electron in like an alkali atom, for example, rubidium-85 or rubidium-87, as in the optical pumping experiment that you may or may not be doing. So that's where you need circularly polarized light to push those electrons up to ever higher values of orbital angular momentum. And the other interesting application is you can use circularly polarized light to create the illusion that you have when you're looking at 3D movies, where you have projectors that project with circularly polarized light, and you have lenses in front of your eyes that pass only left or right circularly polarized light, so that you can see the two images in your eyes that combine in your brain to make the 3D illusion. Okay, so we're just about done here with this short discussion. So If you'd like to check out this spiffy VPython demonstration for yourself, here's the URL where you can download it. Here's the QR code that will also get you there. So, thanks for your attention.